Hello students, welcome to lecture number 11 of computer architecture course. The topic of today's lecture is MIPS instruction pipelining hazards. It's an important lecture and it will be building upon the concepts that you have learned about MIPS instruction pipelining in the last lecture. We will specifically focus on the hazards that play an important role in deciding what is going to be the exact hardware. And we will also see the type of hazards and what are the different solutions to handle those hazards at the hardware level. Okay, so let us get started. So what is instruction pipelining? It is a method of scheduling instructions in order to improve performance. Right, that we all understand that it's a method to schedule instructions in the most optimized fashion so that we could have an improved performance as much as possible. But one thing to remember is improving performance means reducing execution time, and here execution time is the collective time taken to finish a program. That is the time taken to completely execute a program that contains multiple instructions. Some important notes: some instructions take longer to execute than others. It's very intuitive. We don't want cycle time to depend on the slowest instruction. We would like to have 100% hardware utilization. We would like to divide the execution of each instruction into several stages, where the latency of each stage fits within clock cycle of unity, which is one clock cycle, and we would also like to insert registers between each pipeline stages to hold the intermediate results coming from the output of individual pipeline stages. So these are some of the desirable properties or desirable characteristics that we would like to have, and let us see how we can do that. A brief summary of what you have learned in the MIPS pipeline stages. So we know that instruction fetch reads the next instruction from memory, increments address counter, assumes one cycle to access memory. In the instruction decode, we read register operands, we resolve instruction in control signals, we compute the branch target address, okay, if there is a branching instruction. In the execution stage, we execute the arithmetic instructions, or we resolve branches by knowing where to jump by calculating the effective address. Memory operation, we perform load store access to memory, takes branches, again assuming one cycle to access memory. And the write back or register access is the process of writing the arithmetic results to the register file. Okay, so this is a brief overview or small summary of what you have already learned in the instruction pipelining. Okay, so please keep a note of this as we go ahead in this lecture. So far everything sounds great, that we could divide instructions into different pipeline stages to enhance performance. So do we really have a problem now? Unfortunately yes, even though it sounds great, but we still have several problems. So pipelining may give rise to three significant problems which are known as collectively pipeline hazards, okay, or you can also call that as pipeline interlocks. So pipeline hazards could be of three different types. The first is structural hazards, second is data hazards, and third is control hazards. These three individual hazards may result into pipeline interlocking, as a result of which the performance may get hindered. Okay, it may create a bottleneck for the performance enhancement. Let us have a look at briefly what these hazards indicate. The structural hazard says that if two operations require a single piece of hardware at the same instant of time, then it may cause structural hazard. So two operations trying to simultaneously access a single piece of hardware, and that would cause a structural hazard. However, it can be overcome by adding additional piece of hardware to do things in parallel. Second, control hazards. The problem is conditional control instructions are not resolved until late in the pipeline. It takes time to resolve the conditional control instructions. Secondly, requiring subsequent instruction fetches to be predicted. So these two are the problems. Okay, we need to know what is going to be the subsequent instruction fetch. So we should have some prediction mechanism. Solution is flushed if prediction does not hold. Okay, if it's a wrong prediction, then we'll flush out the wrong predicted instruction. And branch hazards can also use something known as dynamic prediction or speculation in order to somehow resolve this process of being late in the pipeline to find out what is going to be the next instruction. The third type is data hazard. It's a data dependency problem where the instruction from one pipeline stage is dependent of or on the data computed in the other pipeline stage. So this is one of the most prevalent problems that you see or come across in MIPS instruction pipelining. So there's a data dependency problem that you have, that the data computed in the previous pipeline would be needed in the next pipeline, and there is a data dependency problem. We'll talk about through an example, it will be clearer. However, there are different ways to come across or circumvent this problem. One of them is reordering, second is forwarding, and third is we can also install or inject stalls inside the pipeline to temporarily have interlocks. Now let us have a look at how a 4-stage pipeline would look like. Okay, instead of 5-stage we can also have a 4-stage pipeline. I'm just trying to give you a scenario where you should not get a feel that only 5-stage pipelining is possible. 4-stage pipelining is also possible. Okay, so that's why this piece of information in this slide is also critical. So in stage 1 you may have instruction fetch, stage 2 you may have instruction decode, stage 3 is instruction execute, and stage 4 is write back. So as you could see, the data memory stage or memory access stage is missing here. Okay, so there could be 4-stage pipelining also. However, you note that before each of the stages you have a specific register to hold the input value and also the intermediate values of each of the intermediate stages, and they all are controlled by the control unit or the centralized controller that you have learned in the last lecture. So let us have a look at how the 5-stage pipelining looks like. Why do we call it pipelining? Okay, in short, the word pipelining means we try to do things in parallelization by breaking the piece of task into subtasks. Okay, so the instruction is broken into 5 different sub instructions or subtasks in 5 stages, and it is run in parallel with the second instruction, third instruction, fourth instruction, and so on. In other words, the starting of the second instruction begins before the completion of the first. The initiation of the third instruction starts before the completion of the second, and so on. So you see that you are trying to do things in parallel as much as possible, and this concept is known as hardware pipelining, that you are trying to break the instruction into sub instructions or subtasks and then trying to do parallelization at the hardware level. Okay, now going by the 5 stages that we know of, IF, ID, EX, MEM, and WB, you can have the first instruction lined up as follows here. The second instruction can start from here, because of course you can't do instruction fetch here, otherwise the same piece of hardware would be used for 2 different instructions, which is simultaneously not possible. So we start after initiation interval, which is known as II, initiation interval, and you do the IF, ID, EX, MEM write back. Then again the third instruction will start after the initiation interval of 1 clock cycle. So it will be IF, ID, EX, MEM write back here. The fourth one starts again with a gap of 1 clock cycle, and similarly the fifth one. So you could see that so much of overlap is happening here in the second clock cycle. 3 sub instruction or subtask overlap is happening here, 4 subtask overlap is happening here, and the maximum pipelining is happening in the 5th clock cycle. So that's why it has been marked in orange to show that the depth of the pipelining is 5 here. So we call this as depth of the pipelining, because the depth of the pipelining is the maximum pipeline that is possible at a particular clock cycle. So this is 5 here, and the total number of clock cycles to finish, okay, the instructions. How many instructions we have? We have 1, 2, 3, 4 and 5. So in order to complete these 5 instructions, you may require 1, 2, 3, 4, 5, 6, 7, 8, 9 clock cycles. Okay, that is just a rough summary of how the 5-stage pipelining looks like. So getting back to the concept once again, you have the instructions in the y-axis and clock cycles on the x-axis, and you are going on with the instructions, okay, in pipeline from left to right with a specific initiation interval gap which we assume to be 1 clock cycle, and you have a pipeline depth of 5, and you finish it in 9 clock cycles for a program which has 5 instructions. The same sort of diagrammatic representation now can be shown using a hardware pipelining or MIPS pipelining circuit or figure. You see that again I have the x-axis in time in clock cycles, which we call as CC, clock cycles, and the instructions. Now I'm giving a specific example. You have these instructions: LW $1, $100 $0. Second is LW $2, $200 0. Third is LW $8, $800 0, and finally LW $8, $800 0. So you have similar type of instructions, and now what you try to see here is that the first instruction loads a value from a specific memory location into register $1. Second one loads it into $2. Third one loads it into $8, and so on. So these have no dependencies, fortunately. So you have instruction memory here, you have a register, you have the ALU, you have the data memory, and you have the register. So the reason for shading it here is that we are trying to read the instruction memory, we are trying to read the register file, we are trying to execute, we are again trying to read the data memory, and then finally we are writing into the register state. So the reading part is given by the right half shaded piece of block. So that's why IM is shaded here on the right half, because we are doing a read. Register same, we are doing a read, so it's shaded on the right half. ALU, we are using the complete ALU, so there's no read write, we are basically just using ALU to compute a particular effective address. So that's why the entire thing has been shaded. In clock cycle number 4, again the right half of DM is shaded because we are doing a read, and in register the left half is shaded because we are doing a write. Same thing for the second instruction, same thing for the third instruction, same thing for the remaining instructions, right? And again, as you see, that we require around 8 clock cycles to compute these 4 operations. We may call this summary as MIPS pipeline data path, but this is just a diagrammatic representation. When you do the pipelining for a particular task, you may not need to draw the entire circuit to do the pipelining. You can draw the summary of each of the blocks and just continue doing the pipelining to find out if you have any particular interlocks in the pipeline stages. Okay, so let us move forward and try to do an example to see how this works. Now you see, if you remember, in the 4-stage pipelining I had some intermediate registers. So the same thing now I insert into the MIPS pipeline data path. So this is the MIPS pipeline data path with intermediate registers. So you have one of the registers that is inserted between the instruction memory and the register file. So we call this as IF/ID register. So this holds all the information coming from the instruction memory and PC and everything. Okay, we'll talk about these registers in details in one of the next slides when we will actually speak about its size and what content it holds. But as of now, just remember that the piece of register here is an output to the instruction memory and PC, and we call this as IF/ID pipeline register. The next pipeline register that we have is between the register file and the ALU. Okay, and we call this as IDEX pipeline register because it is the intermediate register between instruction decode and execute. So this is IDEX, and the content of that, okay, whether we write it, whether we store any executed value, everything okay, that also will be controlled by the controller. Okay, so these registers also have signals coming from the controller. The third stage or third pipeline register is between the execute stage of ALU and the data memory. So we therefore call this as X/mem pipeline registers. This is the third pipeline register that we have, and this is again storing the value of the ALU. And once you have this, then the final pipeline register is the mem/WB pipeline register. This pipeline register holds a value of the data memory and the output of the ALU, and again this is acting as an intermediate register between the last two stages, which is mem and write back. So you see that we have inserted pipeline registers in between each of the stages to hold the intermediate value. Okay, so this data path hardware block diagram that you see of MIPS 32-bit architecture is known as MIPS pipelining architecture with pipeline registers. Okay, now let me do one example. Okay, imagine you have a piece of C code or a piece of function given as A equals to B plus E and C equals to B plus F, and we are assuming that all the variables are in memory and are addressable as offsets from $T0. Okay, so that means the base address is stored in register $T0. Now imagine that we will have to load each of these values B, E and F. So we do $T0 with an offset of 0, we load it into $T1. So LW $T1 comma 0 $T0. Okay, so we will store a specific variable here. Let's say this is B. So B is loaded from memory because these are all addressable as offsets and all the variables are in memory. So we have to load it from memory into the register. Once it is loaded, the second loading will happen in the next location, which is after plus 4 bytes. So therefore we have a gap, and this is due to the MIPS alignment restriction which I spoke of earlier, that every content is able to store 4 byte of information. So there's a gap of 4 bytes, right? 32-bit. Imagine now we are trying to load E. So LW $T2 comma 4 $T0. Now E gets into $T2 register, and now then we will add it. So $T3 equals to $T1 comma T2. So we are adding the content of B and E and storing into T3. Once it is stored into T3, then we again need it to put it back into memory. So we will again apply SW store word, and we will store the content of the register back into a memory location. Let's say this is 12 $T0. Okay, we have stored it into this particular effective address of the data memory, the content of the added value. So A gets stored into this content. Next we will do a load. Okay, now we will have to also load this F. So we apply LW $T4 comma 8 $T0. We can do it from 8 because we had a gap here, so we can load it from this particular location. We assume that the value of F is here, okay, are in memory at this particular location, and it's loaded to T4. Once the value of F is in T4, we can add T4 with the value of B. So B was initially in T1, you know that. So T1 and T4 being added together, and now we again store it, or rather put it up in another register which is T5. Now again store word instruction has to be applied because everything has to go back to memory. So from T5 we will put it back into a new location which is 16 $T0. So store word, and then we will put this content of C into a new memory location, right? So this is the equivalent MIPS code of this particular piece of C code. So this, I am quite sure it is quite clear. Now let us see how to build the pipeline for this piece of program, and if we can detect a data hazard in that. So imagine going by that piece of instruction. I'm just trying to show the first 4 instructions of the entire piece of code. Okay, we may continue doing it for the rest also, but you can easily detect and identify the problem by seeing the first 4 instructions. So the first instruction LW $T1 0 $T0 will have instruction fetch, ID, EX, mem, write back, finishes in 5 clock cycles. The second instruction $T2 comma 4 $T0, Again, after an initiation interval of 1 clock cycle, you start with IF and you finish at WB, which is the second instruction that gets over at 6. The third instruction, add, will contain the information in T3 of the added or addition value of T1 T2. So we have IF ID, and now we need to have an execute, but execution of the value of T1 and T2 can only be obtained after the write back is over, right? So write back of the first T1 is over here, and the write back of T2 is over in clock cycle number 6. But unfortunately we need the executed value in clock cycle number 5. So we insert a bubble here. Okay, this is called injecting a interlock, or we call this inserting a stall. We will have to stall because of an interlock or a bubble. So we insert a bubble or stall here, and then we move to clock cycle number 6. Unfortunately, in clock cycle number 6 we come across the same problem, because T2 is not yet ready. T1 is ready, but T2 is not yet ready. So again we'll have to insert another bubble here and then move to clock cycle number 7. Now it is possible here because both T2 and T1 are ready, so we can perform execute and mem and then write back. Okay, so we are done here. Then we move to the next instruction. So IF ID, okay, these two can be finished. Then we have the execute. Execute can also be done here because execution requires these two information offset and the base address. But after that, then we need to have access to the memory, but in memory we cannot do, because we can only put it into memory once the data is available in T3. Okay, because we will have to put it into the data memory from the register T3, but register T3 is not available until clock cycle number 9. So we will have to keep inserting bubbles in 7, 8 and 9 consecutively. And once this is done, then in the next stage we may have a data memory followed by write back. Okay, so you see that in this piece of pipelining diagram, you have bubble and stalling, and there are 5 consecutive interlocks that you could see. Okay, 5 means 2 here and 3 here, and 3 instructions take 9 cc and 4 instruction takes 11 cc, because we would have a data memory and write back. So you see that this is the problem that we are talking about, and this is called data hazard, because we are depending on the previous data for execution of the current pipeline. Okay, and since the previous data is not available, so therefore we could not do the pipelining here. Fine. So you could identify the problem here, and this is called data hazard. This is one of the hazards that exists in MIPS pipelining. Now let us see how to overcome or circumvent this data hazard problem. So one of the first solutions that you could have is to do something known as forwarding. So we will have the same for the first instruction, second instruction, but in the second instruction what we do, we can forward the information. In the second instruction what we can do, we can forward the instruction from the memory stage directly into the execute stage by having a connectivity between them, because in the second stage the data is available at the output of data memory before it gets back into the register. So data is available here. We don't need the data to be available here and then we can do. Instead of waiting here, we will forward the data from clock cycle number 5 and feed it into the next stage. So IF ID, and here we are supposed to do the execute, right? But execute we cannot do here, because again, as I said, at least we need to wait until the data memory stage is over, because the output will be available at the output of data memory. So therefore we have again inserted a bubble. So this is again a data hazard here. And then, but at least in the next clock cycle we can forward the information from the mem stage to the execute by having a direct interconnectivity between the two stages. So and that is exactly what we did. We forwarded the information, the loaded value from the memory into this, and anyways the first information, which is T1, is available at the output of 5th clock cycle, so that comes here. So using both the information, it can perform execute and then it can go on with the memory and write back. So you see with bubble stalling, which is one interlock, okay, and with the forwarding technique we can finish the entire thing in 8 clock cycles. So 3 instruction takes 8 clock cycles. So we have certainly reduced the number of interlocks with this first solution, and we have also been able to enhance the performance. Now let us have a look at another case of the same example. So in this we again have the same LW instruction finished in 5 clock cycles, the second one finished in 6 clock cycles, the third one instruction fetch, instruction decode. Now we want to do executes. The same problem we can't, so we have a stall or a bubble data hazard. We wait, and then in the execute with one forwarding we can do this, because anyways T1 is available at the end of clock cycle number 5, and this is available at the end of clock cycle number 5 also. So in clock cycle number 6 both these can be used to perform the addition of T1 T2. So execute is done, memory write back is over. Let's say we go ahead with one more instruction SW. In this SW we have instruction fetch, instruction decode, and here now we cannot do execute because already execution is happening. So this is called structural hazard, because we are having a conflict of the resources. So in one clock cycle execution of 2 instructions simultaneously cannot happen, because both instructions cannot access ALU at the same time. So we insert another bubble, but this bubble is for structural hazard. So there is an interlock in this and this, and then again in the next stage, since we can do the execute, we can do the execution, and then we can go ahead. However, since the output of T3 is available at the end of WB, okay, write back, but if we could do another forwarding from execute stage, because in execute stage the data is already available, we can do another forwarding from execute to mem, then we can skip these two and then we can directly get the data from execute stage here. So for after execution we can do the memory, okay, in the we can actually put that information directly into memory, okay, from the register T3, because the content of T3 is available here, okay, and it goes into memory directly through forwarding. After memory we finish at write back. So you see that we are employing 2 forwardings here, one for this and second for this, and with these 2 forwardings we have been able to complete this 3 instruction in 8 clock cycles and 4 instructions in 9 clock cycle, okay, but we have 2 interlocks with 4 instructions. And also one thing you note here is that you have 2 different types of hazards, therefore we call this as dual hazards. One is data hazard type, second is structural hazard type. Now let us have a look at what we can do to remove all these hazards. Is there a way to remove all these hazards? Yes, there is a way. One of the simplest ways is, this is the piece of code that you had. Now if we do something called bypassing or reordering, which is just to shift this piece of line of MIPS instruction up into here and then shift the remaining ones below, then it becomes something like this: LW $T1 $0 T2 LW T2, and then $4 T0, and then again LW $T4, which is this one goes here, comma $8 T0, and the remaining remains as it is. By going with this, you will be able to eliminate all the potential hazards, including data hazards and also structural hazards in most of the time. Okay, so let us see how this bypassing of instruction or reordering of instruction helps you to achieve that. So this is again the pipelining for the first instruction. This is the pipelining for the second instruction. This is the pipelining for the third instruction. Now in the third instruction you see that this T4 does not have any dependency on T1 and T2, therefore T4 can be done as it is without any problems. In the fourth instruction, which is T3, it depends on T1 and T2, and T1 and T2 is easily obtainable at the end of clock cycle number 5. Okay, because T1 is available here, and even if you had a forwarding, still you would have needed it at this stage, so forwarding is therefore not applied. You could easily get it in after the write back stage. For the second instruction, you have the data available at the output of mem stage, so you can get the information from here. Okay, so we may call that as a forwarding, that we have applied a forwarding here. Okay, one forwarding, and you have the reordering done, and therefore in the fourth instruction we can easily do the execute by the output of T2, which is here, and the output of T1, which is here, and we can do the execute, mem, and write back. So you see, by simply reordering and bypassing one instruction in the entire piece of code, all the interlocks have vanished. there is no interlock. So this is a MIPS without interlock. Okay, and therefore this enhances the performance greatly by finishing 4 instructions within only 8 clock cycles. So all structural hazard, all data hazards, everything is vanished with bypassing technique and forwarding technique here. Right, so this is MIPS pipeline architecture or data pipelining, or a pipeline diagram rather, without interlocks, without interlock pipeline stages. That's what many MIPS people define that to be. So this is without any stalling or any hazards present. Okay, now since you've learned about all the different types of hazards and how to remove it, the different solutions and the different techniques to do that, now let us move a little bit into what are those instruction pipeline registers, okay, and how and what do they exactly contain and how do they help in the entire process. In case of IFID, the first pipeline register, it includes 4 bytes, 32 bits to hold the fetched instruction. That is first thing. Second is, if the fetched instruction is a branch, then we also need to pass the new PC so that the branch target address can be calculated in the execute stage. Because if you recall, what was the formula? Target address be 4 intermediate plus PC plus 4. So the new PC has to be also passed on. So we add another 4 bytes in the IFID register to hold the new PC value to be passed to the execute stage. So therefore we have total 4 bytes for the fetched instruction and 4 bytes for the new PC value. So that becomes 8 bytes. So 64 bits is the size of the IFID pipeline register. The next one, which is IDEX pipeline register, we have two 4-byte fields rather, required to hold 2 possible source registers. So that becomes 8 bytes, 64 bits. Okay, because we would like to read 2 possible source registers. So that's 4 byte and 4 byte, 8 bytes. So that gives you 64 bits. Then we have 4 bytes for sign extension immediate value, because in case it's a immediate value, then we need to sign extend that to 32 bits. So therefore 32 bits for that. We also need to pass a new PC value just in case the opcode turns out to be a conditional branching, okay, as in the case of the previous one. So we have another 32 bits. The execute stage also requires opcode in the ID stage, okay, but MIPS prefers to pass the whole instruction. So another 32 bits are stored in the IDEX register for storing the entire instruction. So this becomes 64 plus 32 plus 32 plus 32, and that gives you total size of 160 bits for IDEX register. So that is the size of the IDEX pipeline register, 160 bits, and it contains these 4 information.